Okay, folks, welcome to webinar number 5, series of 9. Topic today is Specification Installation Standards. And again, I think everybody has been here before, so we'll just scroll through all this stuff. Again, a reminder, *6 to mute, then *6 to unmute your phone to manage background noise. Sounds like everybody's muted. If anybody's in doubt, you can say something. Don't hear anything, so looks like everybody's muted. Once again, interject anytime, especially if it's a technical issue or I misspeak. Last webinar, somebody graciously pointed out that I had left my camera on, which was helpful. And I'm not even going to use the camera today. Everybody's seen me. Interject any time, but then once again, every few slides, I have a slide that pops up prompting questions. So I'll invite questions at that time. And then once again, at the end, we'll have time for extended questions and discussion. Could be on today's topic or could be on other topics at that point. Recording it, but once again, not recording you. So I need to remember this time. That means I should paraphrase your questions so that anybody accessing the recording afterwards knows what we're talking about. I think I forgot that last time. I can skip the bio. Everybody's heard that enough times. I think I can skip all this stuff. Those are the different types of people who might be attending. And some of those are required to complete examinations, and this is intended to help you through that. Let's see now where we're going. 1 hour once again. That always seems a bit optimistic, but that was the goal. Previous recordings available. If any of you have been looking for the last two, I haven't quite got them up there yet. Hopefully tomorrow we'll have 3 new recordings, including this one. I don't think I need to show you the Learning Resources page. You guys have seen that. CPD, once again, it's up to you to log it based on your own ethics. According to the CPD policy, we think it's reasonable, 1 point for 4 webinars, ¼ point apiece kind of thing. Learning goals, here we go. So today we're trying to summarize some of the key changes to specification and installation standards and guidelines, key changes from SPM version 3 relative to version 2. Learn to find and apply the standards, mostly apply, because I think everybody has accessed webinar 1, which dealt extensively with how to find things. Quotes are in italics, you might want to follow along. Let's get started. Okay. So, a goal, I think, is that planners and pros need to be familiar with specification and installation standards and guidelines. So this webinar is intended for planners, professionals involved in design, as well as installers. We're including planners and professionals engaged in design because designers have to create specs. We have to create specs in our filing documents, or attachments more precisely. So we need to understand the changes and how to apply them. And we need to provide construction review. Since we certify construction was in accordance with standard practice, in accordance with plans and specs, we need to know what the specs are, understand them, so that we can legitimately sign the letter of certification saying that this construction actually does comply with standard practice. Essentially, I think we need to be capable of oversight, supervision even in some cases, training in some cases, and certainly approving what goes in the ground, or certifying more accurately. So for all those reasons, we need to be familiar with specification and installation standards. Just sort of a commentary for designers, planners, or professionals. I think we need to understand that to stay out of trouble, and that's always our primary goal, is we need to make sure that the installers understand our specs for materials, configuration, and also installation procedures. there's a bit of a debate going on as to whether we even need installers, that maybe any excavating contractor could do installation work because, after all, it's just following our specs. And I personally disagree, because the average excavating contractor doesn't necessarily understand the specs and doesn't understand what we're trying to communicate. So installers, we need to ensure that installers have expert knowledge of SPM specification standards and so on, so that they don't screw up, basically, so they can understand what we're saying. If we make a reference to, for instance, sand needs to meet mound sand specs, we need to be sure that they understand what we mean and are able to find those standards. I think we also need to ensure installers have basic knowledge of SPM fundamentals, like vertical separation, horizontal setback, system selection, problematic soils, and so on. For one thing, if they start construction and find that a portion of the dispersal area, for example, doesn't have the VS that we needed, we sure would appreciate it if they can acknowledge that and give us a heads up and give us a call. Problematic soils, maybe they find some expanding clays or something like that. So back to designers, to stay out of trouble, all of that really means that we have to show up. And sadly, a lot of times that's not happening. A lot of people are more or less selling their stamp and certifying these things without showing up at key stages. We have to attend the site. The guidelines, both from APEG and from ASTT, I think even the SPM lists these, is that we should show up for a pre-construction meeting where we review the site and plans and specs with the installer, and at key stages of the work, which could be, for example, tanks before they're backfilled, dispersal systems before they start laying out pea gravel and sand and so on, maybe dispersal system before backfill, and a final inspection at the very least. This all, of course, assumes that you're not also the installer. Obviously, if you're both the planner and installer, I guess you're going to be attending the site. So some more goals for installers. The reason why we asked installers to attend this is that they need to understand the standards and guidelines to limit their liability, to stay out of trouble, because they share the liability with the planner or professional. If something goes wrong, then the judge or the practice review board will wonder why you didn't notice a drastic departure from something important. And installers need to be able to actually do the work. They need to be able to work professionally, be experts at installation. They need to be able to identify errors and omissions or less than best specs. So again, if they find an error, or they find site and soil conditions that we missed or that we didn't capture in our test pits, installers need to be able to identify that and report it back to the person who did the design. Installers should be able to evaluate and propose alternatives. So if for some reason the location that I indicated for tanks, for example, if it's not working for some reason, access or there's some obstacle, then a good installer will be able to evaluate all that and get on the phone, propose an alternative on the spot immediately, and that alternative will actually make sense relative to SPM standards. The other reason for installers to understand this stuff is that installers also certify construction. Planners and professionals are supposed to get a letter of certification from the installer. It's not filed, it's just retained on records. It doesn't replace the letter of certification from the AP on record that does get filed, but planners are supposed to get that from installers, and those certifications declare that the installation was in accordance with standard practice and plans and specs. So in order for an installer to legitimately make that promise, they have to actually understand what the standards and guidelines are. A bit of editorial here. For all of us, whether we're installers, planners, or professionals, to stay out of trouble, we need to realize how much is required in terms of self-study and compliance We need to be experts at the SSR, the regulation, the SPM, ASTT, or APEG Code of Ethics. They're actually the same, by the way. Every word is the same. And OWRP policy, because that includes a lot of things like policy on oversight of construction, oversight of non-authorized persons, homeowners, and a bunch of other things. It also says thou must follow the SPM. Rope practice guidelines, a whole bunch of do's and don'ts in there. And we need to do CPD, which is what you're doing here, I guess. A little more editorial for installers, and I think it relates to planners and engineers, because we need to make sure that installers know how to stay out of trouble, including get a laser. I don't understand how installers can even pretend to do this work without a rotary laser or some other instrument. Everything has to be on grade, often precisely level, sometimes on a specific slope, and so on. So definitely need some means of differential leveling and establishing confirming elevations. And our installers need to get a friggin' jumping jack. Right? Those of you who attended the workshop previously heard me go on and on and on about this. We need to have something that we can compact the material underneath pipe, make sure it's fully supported. Jumping jack is the right tool for the job, generally. Thicker lifts can handle wet, fine textured soils, and so on. Another thing that we should all heed, I think, whether we're installers or not, is we shouldn't work too cheap. We need to charge enough that we can afford best practices, that we can afford compaction, that we can afford bedding sand, that we can afford the time it takes to properly finish things so that they're ready for grass. We can afford to do testing, including watertight testing of tanks. Sometimes we need to truck in water to make all that happen. So we need to charge enough money to apply best practices. The other thing I think is we need to be able to afford, I guess, to attend the site after construction. I'm thinking about new construction for, say, for example, a new house. I think that installers are very well advised to make sure the owners contact them on moving day or before first use of the system. And the reason is that the installer will bear the primary responsibility for things like paint or drywall mud inside the septic tank. That happens all the time during construction. Damage to the system, that happens all the time. Other excavating folks, landscaping contractors, and so on destroy our stuff. So I think that's a good bit of advice, is to show up before they use it and before all that paint and drywall mud goes through the system. Another topic that we're going to deal with a bit today, the way I put it in truck driver language, is use your own electrician. And sort of the bane of my existence is arguing with electricians that aren't familiar with my requirements. If you have to use another electrician, fine, but good luck with that. You know, I don't think we're asking very much. We want 2 circuits, one for the alarm, one for the pump. We want conduit with adequate size so that we can remove and replace any float or pump without excavating. We need that conduit sealed so there's no migration of moisture and other gases into our junctions or control panels. We don't want any junctions in the tank. Try explaining that to an electrician. And if we do have junctions, they should be above ground, and if they are in ground, which I think is a very bad idea, they need to be sealed or drained, right? Drained with drain rock off to somewhere. So my advice is get an electrician who's you're comfortable with and who knows your expectations. Use contracts. In my role as compliance officer, probably 90% of the investigations and complaints could have been avoided if people had proper contracts that lay out the scope of work, exclusions, schedules, money, that kind of thing. Any questions or discussion on my little sermon so far? Okay. Installer standards. Critical standards are installers' content because they share liability for drastic departures from some critical standards. As a professional, the installer would be expected to recognize departures from vertical separation, horizontal separation, or fundamentals of system selection. So, for example, the setbacks to wells or to any other performance boundary, the installer needs to know that and needs to basically confirm that the system going in the ground meets those key standards. Fundamentals of system selection, in other words, is gravity allowed or not, for example? Do we need a sand mound because we only had 10 inches of soil, and so on. All those things are the topic of the next webinar on Wednesday, which is intended for installers. Those of you who are planners and professional designers, you might decide to skip that one because we're going through those standards which you've already done if you attended the previous webinars. So on Wednesday we're trying to make the point that installers need to know at least the fundamentals of those critical standards. How to find stuff. Here's some more installer standards. 2.3.6 we'll look at in a second, and 2.6. And then the core. And then the corresponding section numbers in the guidelines. So again, most of you are veterans and you've been through webinar 1 and some of the other ones. So just the quickest possible review, I guess, is volume 2. Roman numeral 2 is volume 2, and that's the key standards. Volume 3 is the guidelines, and they have corresponding section numbers. We should sort of have memorized which section is for which thing. So section 5 was the hardcore planning specifications, system configuration, vertical separation, and so on. Section 7 was maintenance, and section 6 is specifications and installation standards. So one of our learning goals was to be able to find stuff, and I guess I'm just going to ask whether anybody has any worries about how to find stuff. Good. As I say, that was covered extensively in webinar number 1. So let's move on. We'll have a look at SPM version 3, volume 2, 3.6. And 3.6 is there. Make it a little bigger. So, some of the key points, it does say install the system according to the drawings and specs. I guess I would hope that sort of goes without saying. But occasionally I run across installers who decided they didn't actually need to follow those things. They actually do. And if they don't, if there's some reason why they can't, they need to communicate and get approval from whoever designed the thing. This is new. Installers then need to keep photographs, the SPM says, and notice that that's a critical standard in volume 2. APEC guidelines encourage photographs. ASTT guidelines, practice guidelines require photographs. It's the best way to stay out of trouble and is a requirement for installers. So that means at key stages of the work, for example, before construction, the tank hole before tanks go in, tanks before they're backfilled with everything all compacted and bedded, scarification of infiltrative surfaces, drain rocker chambers, and so on. You get the general idea. Pick the photographs so that they prove that you've followed standard practice and the plans and specifications. What else do we want to get out of here? When an AP other than the filing AP installs the system, then the owner retains the planner or designer to review the installation, and the installer needs to keep records, but also I think needs to facilitate that oversight. In other words, don't start the job if the planner or professional doesn't know. They need an opportunity to do a pre-construction meeting and attend the site. and keep them informed. In other words, you need to cooperate with the planner or the engineer who designed the thing. The other point worth noting is the installer, assuming he or she is not the same person who designed it, has to provide the filing AP with some information. It could be, for example, the location of something that's going to be backfilled before the planner arrives on site. It could be panel records at commissioning, and of course it could be those all-important photographs. So there was a few things out of this section. I think we captured it. Need to understand that significant changes require filing amendments. So again, if you decide that you're going to move the tank location somewhere else, or even the dispersal system, then that's going to require filing amendments. So you need to understand that and support that and communicate with the person who did the design. You should understand commissioning and what's required, because oftentimes you might be doing all or portions of that without the planner or professional attending the site. So that includes how to flush and test things properly. It includes providing data for the maintenance plan. So I'm thinking about panel records. The maintenance plan is useless if it doesn't have the original panel records that says how many alarm events, cycle counts, and so on. For example, if there's 5 alarms recorded while we were installing the thing and testing it, then the maintenance provider, when he comes back 6 months, a year, 2 years from now, needs to understand how many alarm events were pre-existing. So hopefully it's still 5. Otherwise he shows up, he sees 5 alarms, and he then needs to understand what caused those. So panel record squirt height is another example. That needs to be in the maintenance plan. So installers need to do all those things. Sometimes providing data for the record drawing, and needs to support construction review once again. Just a reminder, *6 to mute your phone, *6 to unmute your phone, sort of manage background noise. Thank you. Okay, 261. That's volume 2. Volume 261. Flow monitoring. Make it a little bigger. So it starts this way, and this is new, so this is important. It's new in the sense that the old SPM said that all systems need to have flow monitoring provisions. And now, as a concession to practicality, it says all dosed systems. It doesn't say all systems. So dosed systems, including pump to D-box, pressure systems, drip systems, and so on, they need to be flow monitored or have provisions to do that. And trickle gravity systems do not, which I think was quite practical. Because in the past, basically, we were required to put in flow meters at the house or something like that. So now flow monitoring applies to all dose systems. The flip side of that is that it actually is required. It always was, but that means that if it's a pump system, we need a control panel. We need a control panel because it has a built-in alarm and it actually controls the dosing, but mostly because it supports monitoring, because it keeps track of cycle counts and so on. So it's not acceptable to put in a pump system with just a high-level alarm. It needs to be a proper control panel that includes a high-level alarm. What else did I have here? I got that, and access provisions. It says this. I guess I'll go to the actual SPM 6.2. It says that we need access provisions for all system components that need routine maintenance. Let's have a look at that in a little bit more detail. That would be 361 flow monitoring. Let's see what the guidelines have to say. It lists a bunch of options on how to do it, including flow meters, even tipping D-box is a way to do it. Tipping D-boxes are kind of hard to find, but it's a way of counting the cycles, because the D-box, you can put a mechanical counter on it, the tipping part of the D-box, and then it tracks how many times that little device tips. And that's a known volume. So that's the way to accomplish flow monitoring for trickle gravity system. And then, of course, flouts and siphons now need counters to provide flow monitoring for them. Float and mechanical counters for dose systems, and control panels with records. Records of cycle counts generally is the easiest way. And there's some other ways, I guess. Access provisions, guidelines. Those access provisions have to be extended up to grade, including tank lids, lawn boxes, and so on. D boxes also need access up to grade. And that continues to be a source of contention with clients sometimes, because they don't really like the idea of having all these green lids all over the place. But it is required, and I think Tim Wilson's advice is good. I know I've taken it. I think it's smart to have some lawn box lids and some tank lids in your truck when you're meeting with the owner, so that you can literally lay out the lids on the ground and basically ask the question, how would this be? You know, is this okay? And if they say, no, that's no good, then you can consider alternatives. The other reason is it just makes sure that they understand that we've had this conversation. So there's no arguing after the fact of whether we can bury these things. Of course, there's landscape features you can put over it and what have you, but they need to be accessible to grade. It also says that maintenance should not involve entering a confined space. More on that later, but essentially all the valves and unions and filter handle extensions all need to be within 15 centimeters of the top of the riser or the lid. It's still odd to me that a lot of people are missing that point. I was looking at one just a week and a half ago where the union was 3 risers, maybe 4 risers deep, 3 or 4 feet deep. So that's not very helpful. You can't pull the pump out if the union's out of reach. Let's move on then. Where else are we going? Appropriate access to what? To all serviceable points, including observation ports, infiltrative surface observation ports, monitoring wells, if any, for groundwater monitoring, lysimeters and other in-ground provisions. Those are a type of sampling device for drawing a sample out of soil, which we need for combined treatment and dispersal systems, amongst other things. So we need to have lawn boxes or some kind of access provision for all those things. Lids of all tanks, every lid, every inlet and outlet. Filters, obviously, need to be accessible. Control panels need to be accessible. D-boxes, people are still missing that. D-boxes can't be buried. They have to have an access riser to grade to support maintenance, inspection, confirming flow splitting to each lateral, cleaning out the D-boxes of debris, and so on. All the valves, including fancy stuff for drip, including backflow prevention valves, air vacuum valves for drip, and so on. Indexing valves need to be accessible. Cleanouts, we need cleanouts for sewer lines. Force mains need a cleanout. Pressure laterals need a cleanout at the distal end. Interceptor drains, in other words site drainage, also needs cleanouts, all with access boxes. And those need to be exposed flush or above finished grade. Adjacent ground slope to direct surface water away, otherwise they fill up. And we need unions. We need unions for obviously the pump, but also for if there's check valves down the line, down the force main or at laterals to prevent drain back or other. Another example is indexing valves need to have unions so that we can remove them. I had something highlighted previously here for control panels. They should be located in external locations or in a service building that'll actually be accessible to the maintenance provider, and preferably within line of sight. So not in the crawl space. Preferably they are accessible outside and within a few steps of the pump chamber, because at maintenance time you need to be able to look in there and do things, including confirming that the pump's operating and draw down and all that sort of stuff. So ideally the panel is a few paces away from the pump chamber. Let's see if we captured everything there. I think we did. Pictures. Pictures are always good to break it up. Access provisions. The green lawn boxes is what we're talking about for valves and cleanouts. And you'll note that for valves, lateral isolation valves, the lawn boxes are too short, almost always. Sometimes, I guess it's possible. I think they're about 9 inches tall, so if you only had 9 inches of cover, you might be able to get away without the extension. But generally speaking, we need to have these extensions so that you can actually reach in the lawn box to access the valve. Lawn boxes are too short, basically. And boy, I sure find that a lot. There's a lawn box, but you can't get at the valve because all the pea gravel or drain rock has run around the valve. So those are 6-inch, cheap, doesn't have to be CSA approved, just cheap drain line, ASTM stuff. And again, to repeat myself, those are generally required to extend the lawn boxes for lateral isolation valves and maybe some other things sometimes. Another picture. Every access provision in a tank needs a riser to grade. In this case, there's a lot of them. Big job, obviously. What else do I want to say about that? They need to be extended to grade. These risers are kind of slick. You know, a lot of us use the Polylock or other type of riser that is in 12-inch or 6-inch multiples. This type is handy because we can cut them to whatever elevation we need. Otherwise, it's a little bit of math involved in equalizing all of our tank excavations, the elevations of the tank excavations, so that the risers all end up, or the lids all end up at exactly the same height, multiples of 12 or 6. So these are quite helpful. If you're really paying attention, you might notice that they're helpful, but this is actually the wrong type. This is spiral lock. It should be ultra rib. This spiral pipe is a real bugger to cut square with a cutoff saw. Ultra rib has ribs that are parallel to each other instead of spiraled. And on this job, it was just because they didn't have it. So we ended up with this stuff, and it was a nightmare trying to cut that with a chainsaw type cutoff saw in the field with a nice square cut. As you probably know, in here there's an adapter ring that fits on there and some adhesive, and then the lid screws onto that. Well, what else have we got for access provisions? Treatment plants have access lids in this case. Yeah, that's probably enough. Lawn boxes, lots of them, and they are a pain in the butt. They're difficult to backfill without damaging or losing their position. They certainly are a pain in the butt for us, and they're a pain for the owners afterwards. Comment about the height. In this case, the height was intended to allow for topsoil. In other words, a couple inches of topsoil is going on this site. In my own experience, if you leave them too high, the lawnmower catches them and destroys them. And if you leave them too low, then the grass grows all around them and you can't see them and can't get at them. So my personal view is, something like a 1/2 inch, if that, above finish grade is important. So all these things, not only were they a pain to backfill, but they also all have to be set with a laser, right? Because these things are not at the same elevation. They're meant to support a crown in the finished cover soil. So, you know, these two are probably the same elevation. This one's a little bit lower, and this one's a little bit lower again, if you get the general gist of this. So certainly a pain in the butt, but we need them. And any questions on that stuff, any chance? Everybody okay? Okay, moving on. 2.6 then has the specification and installation standards, and let's go there. 2.6, and I was looking for 6.3.2, which deals with pump discharge to the septic tank. So that could be for a lot of reasons. It could be a deep basement where you know, a portion of the sewage is pumped up into the septic tank. Could be a remote building, you know, a mobile home on the other side of the lot, or a cabin, or it could be a lot of things. But it's when we're pumping sewage into the septic tank. And a couple of key points. It's not really new. I think it was always this way. Grinder or macerator pumps, we have to increase the septic tank capacity by a factor of 2. The idea being more retention time for settling, because grinder or macerator pumps increase TSS. At least they increase TSS in the septic tank. You know, it's still the same total amount, but there's more of it finely ground up, more likelihood it's going to escape the septic tank and end up in our soil. So we need to increase, we need to double the size of the septic tank if we're feeding it with a grinder pump. This is interesting, I think. If only part of the sewage flow is pumped, you increase that proportion by 2. So for example, if you had the upstairs plumbing leading directly into the septic tank by trickle gravity and the downstairs being pumped, then you don't need to increase the septic tank by a factor of 2, just some corresponding proportion, if that makes sense. Just a word, just for fun, I guess. Grinder pumps, you know, there's a different kind of thing called a sewage transfer pump that can handle typically up to 2-inch solids. Not a grinder, just a sewage transfer pump. I've used them before, but they're prone to trouble. You know, tampon strings or other debris, you know, chicken bones and teddy bears and what have you, will not go through those, whereas a grinder pump is more likely not to clog. So my preference is to use a proper grinder pump. But if you are using a sewage transfer pump, first of all, you've created a maintenance headache because it's going to fail. But the other thing is, then I don't really know what to do with this. You know, there's no doubt in my mind that a sewage transfer pump also increases suspended solids, you know, smashes things up. But do we then need to increase the septic tank by 2? I don't know. I think we need to increase it by something because of more suspended solids. But oddly enough, the SPM doesn't actually tell us precisely what. So we'll move on. What else did I have here? We had increased tank size. Pump discharge is a peak event. In other words, if the pump turns on from the mobile home on the other end of the property and discharges to the septic tank, that is a peak flow. So we need to manage peak flows. Ensure peak flow to the tank will be less than that defined for normal residential sewage. And we won't necessarily go there, but that goes back to that section we looked at a few webinars ago where it gave quantifiable parameters for residential sewage. And right below that, it deals with peak flows. The important thing, I think, is to note that we don't want to put in a dose that's excessively large because it stirs things up, right? So one option is to go to that table in volume 3. The other is just to understand the concept and make sure that your pump dose volume into the septic tank is quite small. Same thing goes for treatment systems. Too much peak flow just disturbs things. The next point on my slide, I'll just go here now because we've got it in front of us, is that if you have pump discharge of sewage to the septic tank, not to the dispersal system from a pump chamber, but pumping sewage into the tank, then we need another alarm. We need an alarm because, well, for one thing, if the effluent filter is clogged and we're pumping in 20 gallons of sewage, that's 20 gallons of sewage that's going to back up into the house, right? So we need an effluent filter alarm if we're pumping in there. Personally, I think those are a good idea in any event because people don't clean their filters, but we actually have to have them as a critical standard if we're pumping sewage. Hopefully that makes sense because the consequences of the backup would be huge. Rather than just a trickle coming out of the lowest shower or the lowest toilet or something, we're going to have a whole dose backing up into the house and making a bigger mess. The other thing here is that those sewage transfer basins or whatever it is we're pumping from needs to meet pump chamber standards. That's new. So that means that it needs to have flow monitoring, it needs to have proper floats or transducers, and most importantly, I think it needs a reserve volume. Right? It needs an alarm reserve volume to prevent backups into the house if that sewage transfer pump fails, or more likely when it fails. Tank venting is another issue. The minute we're pumping stuff, we definitely need to think about vents to receiving tanks, intermediate tanks, and so on. The one installer I work with caught that issue, and that's why we want installers to know stuff, is we had all the sewage being pumped into the septic tank. Normally a septic tank vents, as you know, through the inlet pipe, the 4-inch inlet pipe, back up through the roof stack, through the plumbing system. But when I have a force main coming into it, there's no vent. And I had totally missed that in my design. Installer calls me up and says, "Hey, dummy, you don't have a vent." And I go, "Thank you very much. How about put one in?" And he did that, right? Which was basically a 2-inch pipe leaving the septic tank to a gooseneck up behind a shed next to the fence kind of thing. So we need to make sure we have vents anytime we're pumping sewage or anything really. Pump chambers for the dispersal system, they're generally vented because there's a 4-inch pipe going from septic tank to pump chamber, and then it can vent back through there. But obviously as we're pumping things, liquid levels go up and down, so it needs to discharge air and suck in air as all that is happening. Let's go back to the slides, see if I missed anything. We got alarms, dosing chamber and septic tank. We got venting. What else do we got? 632. 632, moving on. 632. Okay, 632 says refer to volume 3. So let's do that. Volume 3, 632. A whole bunch of stuff highlighted in advance here. So it mentions things that we should all already be doing, basically. Pipes need to be properly bedded. Minimum of 6 inches on all sides, it says. Sure. I include that as a specification in my filing documents because I mean it. You know, if the native soil happens to be clean, and I specify a particular size, then you can use it. But more often than not, we need to import some bedding sand. And I find it amazing that people will put in a system for $15,000, $20,000 or more and are too cheap to buy a load of bedding sand. Excavating guys that should know better. We wouldn't put in a water line or a sewer line to a house in the city without bedding sand. So why are we doing it in our drain fields? All piping should be watertight, sure. Properly supported on compacted material or other reliable fashion. Maintenance providers find that the vast majority of jobs they go to for the first time, the inlet pipe and possibly outlet pipes of tanks is bowed. And a bowed pipe creates all kinds of problems, including the venting problem. If it's bowed enough that there's a water slug in there, now you have no venting. concrete degradation and so on are some of the problems there. The other problem is solids accumulations. I got some great pictures, I should have thrown them in here, of a bowed pipe, and in the bow it just created a big blockage of fats, oils, and grease. Now there might have been a usage issue, but if it wasn't bowed, all that stuff would have ended up in the tank. So a bowed pipe is really, really bad, and that means we need a jumping jack, and we need granular material like bedding sand or native soil that's not crap, that's not wet clay, for example, something that'll actually support the pipe. We don't necessarily need to get 95% Proctor or something like that for you excavating guys, but we do need to make sure it doesn't settle more than a 1/4 inch or so, and that requires compaction. It requires the proper material and suitable depth of lifts. Typical septic tank, maybe the pipe is 4 feet or so above the bottom of the tank. So again, we don't have to get 98% Proctor. We're not building an airport, but we do probably need 3 lifts. 3 lifts for a 4-foot fill, and a jumping jack will handle a very thick lift. If you're using a little plate packer, then you need 6-inch lifts, so forget it, get a jumping jack. Other reliable fashion is rock. We could fill up the void underneath the pipe with drain rock or other rock all the way to the bottom of the tank excavation, because rock doesn't really need compaction, right? It's not going anywhere. It doesn't take a lot of rock. We can backfill with soil, creating sort of a V shape, and then it's 1 bucket full of rock will do it, or 2 maybe. And that does need to go all the way to the bottom of the excavation. We had one investigation, the guy got himself in trouble, the pipe settled, and he thought he was solving the problem by putting 6 inches of pea gravel under the pipe, but the soil underneath that was clay, all uncompacted, so he just totally missed the concept. It's not 6 inches of rock, it's rock all the way down to the bottom of the excavation. Heavier wall pipe, forget it, that doesn't work. Heavy walled pipe settles just as much as drain line does. Other reliable fashion, some people are trying to dig their tank excavations so tight that there's only 6 inches or a foot of undisturbed soil. Good luck with that. I think it's not worth the time. You still need a jumping jack sooner or later, and I'm not even sure it works, because if the gap is more than a foot, say if it's 1.5 feet, it's still going down. So the point is proper compaction. Get a friggin' jumping jack. We got the pump systems again, grinder pumps again. This bit down here, protect pipes from breakage under driveways, for example. So that could be a pipe sleeve. And a pipe sleeve is a bigger pipe over a smaller pipe. So it could be, for example, 4-inch drain line, the white stuff, surrounded by a 6-inch SDR28 or something like that, thicker walled pipe. And that also works for frost protection, at least to some degree. So we need to protect pipes from frost, and this new SPM has a lot of content on freezing issues. A little more on that later. Could be adequate soil cover or suitable insulation. And under a driveway or a roadway, as a lot of you know, especially those from the north, there's a tendency of that to drive the frost down, so that the frost will go down many feet, and that won't happen to the same degree on soil that's not being driven on. So there was some new content. Back to my slides, see if I missed anything. Proper bedding and support. Protect pipes both structurally and from freezing. And here's what we mean by bedding, right? Typically, the way I do it at least is dig the trench, throw the pipe in, throw some sand in, and then lift the pipe in the sand. But the pipe has to be free of bows, it has to have enough sand under it, and this picture is hopefully conveying the idea that it's on perfect grade. Right? So it's got bedding sand under and over. Right? In this case, the tape, in case that's distracting you, is because the wiring was going down the same trench from the house. And it doesn't really look like the neatest job of bedding, but it is what it is. Hopefully we got enough bedding over top that we're protecting the pipe. Fully supported pipe. So hence the jumping jack in the picture. So the idea is that all this material, all this stuff in here needs to be compacted in lifts, needs to be suitable material, especially with this configuration, because this pipe, if the soil goes down even a very small amount, it'll be messed up, right? If the pipe goes down, the effluent filter in here is going to be skewed and won't be able to get it out. Bad things are going to happen. If it's a straight shot between tanks, that problem is less pronounced. And I do this all the time, wrapping it in that way so that the pump chamber is close enough to the wall that the float and pump wires will actually reach the control panel. So it's a very common approach. There is no added risk of clogging because the water or the effluent in this pipe is filtered, right? There's no solids in it. In fact, didn't even need 45s. Could have done it with 90s, right? What else do we want to say about that? You know, while I'm at it, I personally put sand on top of the tanks as well when we have rocky, gravelly soil, especially poly tanks. Probably enough said. We're talking about pipe sleeves for two purposes, one for structural integrity and the other for frost protection. A lot of you have seen this picture before. This is from the big job in the Blue River. Very cold climate, engineers all over the place, and this pipe sleeve is, shall we say, overkill. It's probably appropriate for a $500,000 system though. This is a very thick-walled steel pipe, so it definitely deals with a structural problem. There's 100 or 200 trucks a day driving over this thing. This is a bulk fueling station as well as a restaurant, truck stop, and so on. So it's very appropriate to do something to protect the pipe, its structural integrity, and then also from freezing. So the sleeve itself helps. Inside the sleeve will be a 4-inch pipe. It helps because of the airspace, right? There's going to be an airspace, and that's going to start heating up because of the sewage running through this thing from a restaurant and so on. And then, of course, I guess, obviously, insulation up the sides. There'll be insulation over the top. This polybutyl liner is an insulator. Really, that's its purpose, is to provide sort of a frost break. In our scenario, for typical residential systems, this conduit is probably going to be something way cheaper. Like this was $8,000, I think it was, for that hunk of pipe. It'll be a couple of pieces of SDR 28 or something like that. The liner can be just a piece of construction poly. That really helps under a driveway. If we're putting pipes underneath a driveway, is a layer of, I don't even know how many mil, just the conventional poly you buy for holding insulation into walls and so on, is very effective at stopping the frost from being driven down. Next picture is the same thing from the other angle. A little further on, you can see the insulation, and then the liner gets wrapped over top. You get the gist of this. This is a common thing to protect pipes from freezing, and in a significant part of the province is a hell of a good idea. Some more insulation, protect from freezing. It's just styrofoam SM thrown over. One little snag, as per the previous picture, is it needs to be perfectly flat, right? The sand underneath needs to be perfectly flat, otherwise the styrofoam just breaks up. And of course you can't run a jumping jack over it until you get 1.5 feet of fill on it. That's another story. So styrofoam SM, we do it for piping, and we also do it over top of tanks and down the sides of tanks. And believe me, if you don't, you get frozen tanks. I got all kinds of pictures of pump chambers that look like popsicles. Freezing is a significant problem in many parts of the province. These were poly tanks, and this is a pretty cost-effective way of doing it. We could have put styrofoam SM over, but most towns now have some local guy who has a pickup with spray foam gear, you know, and spray foam over tanks and risers, I think, works excellent. So that's what that is, spray foam insulation. Hey, Shush. We're not covering... Sure would be if we were, but we're not. Good point. I'm glad you asked the question, because that's an important point, is do not put styrofoam over top of the dispersal trenches. Yeah, good point. So this is over the force main. Although the force main drains, it drains slowly, and it gets really cold up here. So while it's draining, we wanted some insulation. Very good point is do not put this over top of the dispersal trenches, and neither do we need to. As you said, we don't want to because it chokes it off from evapotranspiration and oxygen flux, right? And over the dispersal laterals, we don't need to, because the strategy for those is to drain them, right? Every third hole pointing down, for example, or even every hole could be pointing down for that matter. Good point. You know, there's some insulation on the access provision for indexing valve. So insulation. Again, this is just over the tanks, not the dispersal system. So let's move on, see if we can find any new stuff in this section. We'll look for effluent filter and filter alarms once again. And the section is 6.4 tanks. So this basically says that we do need an effluent filter. It doesn't say that directly, but that's the intent. We actually do need an effluent filter, and there's the spec for it, 1/8 inch. And effluent filters are the best thing that ever happened to the wastewater industry. They will make a huge difference on the longevity of the system. The downside, of course, is that there's a tendency to not clean them. They become a maintenance issue. What else have we got here? We got effluent filter. Intake of the filter has to be in the clear zone, obviously. Once again, we need a filter alarm when sewage is pumped in. The filter needs to have adequate capacity that it'll last for 2 years. Effluent filters come in $15 versions and $150 versions. And the $150 version is worth the money. For one thing, it doesn't clog within 2 years because it's huge. For another thing, it does a very good job with results better than 1/8 inch, which prevents soil clogging. And that was my comment, that they're the best thing to ever happen, because they're going to make our dispersal systems last much, much longer. So personally, the ones that come with the septic tank, I throw those out or give them back to the truck driver and put in one that's better. Quick reminders. Yeah, go ahead. No problem, *6, thanks. Pump discharge from a septic tank. This is all new. And I'm not impressed, frankly. What it is, or says, is we can now put a pump in the septic tank. Yeah, I know. I don't think it's a good idea, because we're raising and lowering the scum layer. Every time the pump kicks on, we're increasing the flow velocity from first compartment to second compartment, or just in general, we're stirring things up, which kind of defeats the purpose of the septic tank, which was to let things settle out. But it's now allowed. And we'll see a diagram in volume 3 here in a few minutes. But it needs a pump vault, a screen pump vault in the second compartment or next to the outlet of the septic tank, and then we put the pump in there. And those pump vaults are a real pain in the butt. For one thing, they're big and heavy, and at maintenance time they need to come out. Right? So that means pulling the pump, pulling all the floats, pulling the pump vault to get this thing out. Then there's all these standards. So if you decide you're going to put a pump in a septic tank, you need to have a maximum pumping rate. The drawdown has to be less than 10%. You still need an alarm reserve, which now means you need a bigger septic tank. So for all those reasons, I don't think it's worth it. And to repeat myself, I think it's dumb. I think it increases suspended solids, but that was up to folks other than I. Let's see if I can find a diagram of a pump vault. This is in version 3. There you go. There's a pump vault version 3. I meant to say volume 3. So a lot of you have seen those things. Those pump vaults are a great big thing that filters the effluent before it hits the pump. Pain in the butt if you ask me, but once again you are allowed as long as you follow all those related standards. While I'm here, I think everybody here is reasonably experienced, but here is a diagram of a septic tank properly configured. Where do we want to start? I've seen this go horribly wrong often. This inlet and outlet baffles actually need to extend into the clear zone. I often see inlets or outlet pipes that don't have a T and a baffle on them at all. So now the discharge comes in and disturbs the scum layer. I've also seen these, real good one once. Ron Hine and I were up looking at a complaint, and the poor bastard, he had this extended all the way to the floor. It's just bizarre. It must have been a crooked cut right on the bottom. And when we asked him, he said, "Oh yeah, I always do that." "Well, why do you do that?" "Well, it prevents things from distorting." And I'm thinking, are you friggin' kidding me? You know, the solids need a way of getting out of there, so you can't extend it to the bottom, for one thing, because this is going to build up with sludge, right? So they need to be properly configured. They do need to have a flow-through opening. Select all. Right there, again in the clear zone. Some tank manufacturers do this with a couple of baffles with T's and stuff, and that's okay, I guess. They do need a filter with a properly configured baffle drawing from the clear zone, and they need a handle extension to within 6 inches of the underside of the lid, which we have to install because they don't come that way, right? What did I just do there? Sorry about that. Okay, move that aside. And they need access lids exposed to surface, and the ground needs to slope away. One guy who's in trouble right now, the reason really was that the ground was sloping towards the riser. The risers are water resistant, not necessarily waterproof, and so the ground needs to be sloped so that surface flows don't gather around the riser. They need to be sealed. Groundwater infiltration is a big deal, and so on. I guess that's enough there. Let's see what I missed. Pump discharge from septic tank now is allowed, even if it's a bad idea. You really do need baffles, and the volume of the septic tank needs to be 3 times DDF. I think I missed that. That is, there it is, it's on the next page. There it is. Specify a tank working volume at least 3 times DDF, unless we need to increase it because we have a macerator pump or a grinder pump, or unless we're going to reduce it if it's upstream of a treatment plant. So if it's upstream of a treatment plant, it's not a septic tank, it's a trash tank, and typically the manufacturers want something like 1.5 times DDF, which is fine. Oftentimes I put in a trash tank even if the manufacturer doesn't require it, for one thing, for pump out frequency. Sometimes the settling compartment in a treatment plant isn't big enough, arguably, so it needs to be pumped out too often. In other words, I think a trash tank is always a good idea, but I digress. So septic tanks need to be 3 times DDF. What else did we have here? Next slide. Tanks continued. We had got to check that they're watertight and have to check that they, well, I almost misspoke there. Let's have a look. 6.4. That'll be on the next page for tanks. So it says ensure all tanks are watertight. That means we have to do watertight testing as per volume 3 guidelines. We have to fill the thing for 24 hours make sure it doesn't lose more than, I think it's 0.1% of the volume. Pain in the butt, often need to truck in water for that, but there it is. And then this is important. They chose this language extremely carefully. It does not say ensure the tanks meet the CSA standard. It says check. And the reason was that some manufacturers of tanks don't have CSA certification. You know, American tanks for one thing. So it says check, not ensure. In other words, they're trying to tell us to consider the issue, make sure the thing actually is structurally sound, but there is no requirement for certification of septic tanks in BC. Interesting, I know. Then it talks about risers once again. We do actually need a riser for each chamber, filter, baffle. There's some specs on the size of the thing. It has to be extended to finished grade, has to be sealed with a child-resistant lid, in other words, screwed in place. Once again, all the serviceable stuff needs to be extended to within 6 inches of the lid, the top of the riser. Unions, valves, filter handle extensions. Let's catch up on the slide. Risers, everything within 6 inches. Wonder if I need to. No, I'll have a picture coming up. I was going to explain that the plumbing then actually comes up from the pump, up into the riser, and across and back down again to a lower discharge point. Photo coming up. A little more stuff on tanks. See, we got once again bedding, fully supported, access to grade, watertight testing, and risk of tank flotation and venting. So I think we've talked about some of these issues previously, but let's see where we're going. That is 2.6.4. There again was all the bedding stuff. It mentions compaction once again. It mentions support pipes so they don't settle once again. So in other words, if your pipes are going down because you don't have a jumping jack, then you're in non-compliance with a critical standard, and you'll be held to account. It talks about the risers again, insulation. It talks about testing all tanks, less than 0.1% loss. Volume 3 has a bunch of guidance on how to do that. Test the tank penetrations and the lid seal. Also mid-seam tanks are prone to leakage. Got to seal all those penetrations. One guy I know, he put in his 2 tanks. They were the same tank. So he was trying to get 2 compartments out of 2 individual tanks, which is completely allowed. But they were the same tanks. Therefore, the outlet of tank number 1 was lower than the inlet of tank number 2, because he excavated them on the same elevation rather than stepping the septic tank down. So he smashed a new hole in the wall and put a pipe in it and tried to grout it up, and grout doesn't work, period. So groundwater infiltration caused a complaint, practice review board, and so on. So we've got to make sure everything's sealed. Then we have this issue, the whole risk of tank flotation. And some people don't even believe it can happen, and other people it happens all the time. I can assure you it happens all the time, especially when tanks are pumped out. Pump chambers are often almost empty in their normal operating condition because most of it's alarm reserve. And they pop out of the ground when groundwater level rises, including concrete tanks, and especially the lighter and more slippery poly tanks. Happens all the time, and it's a disaster, right? It costs way more to fix that than it did to put in the tank in the first place, by far. It depends on how much soil is on top, depends on how high the groundwater comes, but that's one reason why we have a 0 meter setback from tanks to perimeter drains, so that we can make sure that the sewer outfall from the foundation comes out above the footing, in other words, through the crawl space or basement wall, not under the footing, and then we can dewater the top third of the tank just using the perimeter drain around the house. Or we can put in a drainage system, or we can put in anchors. But this is an important point. What else do I want to say about it? If you're skeptical, a concrete tank is heavy, especially if it's got a foot of soil on it. Sure, a battleship is heavy too, right? But it floats. So septic tanks pop out of the ground all the time. It mentions tank venting again, and we've more or less been there and done that. But a few things, you got to ensure venting doesn't create a odor nuisance or explosion hazard. So if you're doing venting, you need to run it to a place where that air isn't going to, has less chance of being a nuisance, assuming it's not going out the plumbing stack of the house. The way that a lot of us are doing it is in ground, in the soil venting. In other words, we run a pipe from the treatment plant or whatever, septic tank or whatever, into a trench that's above the seasonal high water table with a couple of chambers, gravelless chambers, right? Like 3, 4, 5 chambers long with permeable soil over top of it, not clay. And then the soil, if it's porous, if it's permeable, allows air to go in and out slowly and controls odor. It controls odor extremely well. So that, personally, I think is the way to do venting, is underground. If it's not underground, if it's a gooseneck, then we're supposed to put screens in place for pathogen vectors, basically, so we don't get animals or insects going in and out of there, which can cause problems, including transmitting disease. Yeah, that's probably enough on venting. 2.6.5, back to that. 2.6.5, the next section in Volume 2. It deals with a bunch of important things. It includes an aggregate spec that might be new. Aggregate needs to be clean. Aggregate, by that we mean drain rock or pea gravel, right? So there's the spec. So I cut and paste that spec, or that standard rather, into my specs so that the installer needs to ensure it's that clean. And that really is very clean. Typically it's thoroughly washed and hence more expensive. The issue is silter clay migrating to the infiltrative surface and contributing to soil clogging. So make sure you buy clean drain rock, check it before it leaves the truck, right? First load, get up on the sideboard, put your hands in the drain rock, wet, and there should be no clay sticking to your hands. Enough said. Separation layer, lightweight non-woven geotextile. This is new. The old SPM didn't make it clear. We're talking about the separation layer between the drain rock and the cover soil to prevent the fines from migrating down through the drain rock. It should not be high-grade geotextile. It should be non-woven so that the fibers are random, not woven in a cross shape, if you know what I mean. The good stuff is too good. The good stuff will tend to become a clogging layer, won't allow evapotranspiration up and oxygen flux down because it's too tight. So what we're talking about here is the cheap stuff, the stuff from Walmart or Canadian Tire that you can see through if you hold it up to light, not the good stuff. Personally, I use untreated building paper. It's that gray craft paper that they use underneath subfloors in houses. It's just sort of cheap newsprint kind of stuff. We used to literally use newsprint, and the idea is that it does rot and disappear within a season. In other words, it degrades and turns into nothing very quickly, and that was the intent, because by that time the soil, the cover soil, is consolidated enough that we don't have a lot of migration of fines. That's my preference, is untreated building paper, because even the lightweight non-woven stuff, it tends to clog things. When you pull that up 10 years later or expose it and look at it, it'll have a layer of fines on it, worm poop and soil and all kinds of other things. So personally, I don't like the idea. I like the untreated building paper, so we get lots of evapotranspiration up, oxygen flux down. There is such a thing called a graded aggregate and sand filter layers. And just to explain what that means, that would mean if you had drain rock, say 3/4 inch drain rock on top of your pipes, then graded aggregate means then you add a layer of pea gravel, and then what's the word I'm looking for? Smaller gravel, bird's eye, and then a layer of sand. So none of us are going to do that, I would assume, because that means 3 types of aggregate trucked in and 3 placement and leveling stages. It's kind of insane. It'd be very labor intensive, very expensive, but that's what it is. So make sure you use something. You do have to use some separation layer, and my advice is untreated building paper, although you could use cheap geotextile. Let's move on. What else did I have in my slide here? Separation layer. Cover soil. There's standards for cover soil and the permeable fill for tow blankets and so on. So let's have a look at that. We're still in the same section. Cover soil, it says use permeable native soil or loamy sand, loamy fine sand, or sandy loam. So if the native soil isn't one of those, don't use it. In other words, don't use clay, right? Or even some other soils that are quite fine, because again, it chokes it off, right? It's absolutely critical to have evapotranspiration up, oxygen flux down, otherwise the thing won't work. So cover soil needs to be the right stuff. For at-grade beds and sand mounds, it's those. Again, promoting oxygen porosity. We do have to ground and grade the cover soil to shed water, so that means no ponding. That means that installers actually need to know what they're doing and have a friggin' laser and a good eye and be good at a rake. These things need to be landscaped properly. No dips and doodles, no ponding. Pictures of that coming up. We have cover soil depth has to be 10 cents to 30 cents after settling. So no more than that, unless more is needed to provide protection from freezing, in which case we have a maximum of, I think it's 45 centimeters. You don't need more than that, no matter what part of the province you are, because you're going to drain your laterals, right? If you're doing that for frost protection, then the part of the cover soil that is in excess of 30 centimeters needs to be mound sand, right, or clean coarse sand. Feel free to ask questions on that, but it's probably fairly self-explanatory. The permeable fill, it could be between chambers, for example, or it could be for toes of sand mounds and so on. Does not have to be mound sand, but neither should it be clay. I made that mistake once. Did a raised system, trucked in a bunch of fill from down the street to extend the toes. The fill from down the street, the reason it was free was because it was junk, right? It was clay. That's what everybody wants to get rid of. So I created a bathtub, and it just basically made effluent break out at surface because there was no place for it to go. So two-sided coin. One is make sure it is permeable. The second is what a blessing it is that it doesn't actually have to be mound sand. It can be, a native material that has reasonable permeability. Which is important for sand mounds because that's a lot of sand. Let's see what else I had. Any questions or discussions on that part? That was quite a mouthful. Anybody? I could almost use the break. I almost wish somebody would ask a question. No way. You guys are no fun. Moving on. Gravelless infiltration system, which is fancy talk for chambers. So some new standards there. This one isn't new, actually, it always was. The actual width that we use for determining our area of infiltrative surface is the width of the chambers. The actual width of the chambers. So not to promote any particular product, but I guess in order to make my point, I have to mention infiltrator. Infiltrator chambers, one model is EQ36, meaning that they claim it's equivalent to 36-inch wide infiltrative surface. First of all, it's not. That was a dumb idea in the first place. is a marketing ploy. And secondly, the SPM now says that we can't do that. The EQ36 are not 36 inches wide. They're only a little over 2 feet. So you have to use the actual width of the chamber. And let me prove it to you, I guess. Gravelless infiltration systems. Effective width is outside dimensions of the base of the chamber. The other thing that's going to come up next on my PowerPoint slide is do not cover chambers with a separation layer like fabric or untreated building paper or anything like that. Infiltrator will void the warranty if you do that. The only time to do that is if you have real fine sugar sand, and then you have to use the stuff that Infiltrator or ARC recommends, and it's very porous. You know, it's not hydrophobic, as the term goes. So don't cover chambers, right? The idea is that the chambers are manufactured in a way that will prevent soil from infiltrating it or going inside of there. So no fabric over chambers. Backfill, once again, permeable soil, permeable or more permeable than native soil. This is new. This is observation ports for chambers, right? This is for gravelless systems only. One observation port on each lateral, and by observation port we mean something that you can, a maintenance provider can assess the clogging effects on the infiltrative surface, look in there to see if there's any ponding after a dose. And we need one for every lateral for chambers, oddly. We only need 2 if it's drain rock trenches or a drain rock bed, but we need 1 for each lateral. And as you probably know, there's a pre-scored position on top of the chamber to make that happen. In other words, it's a 4-inch pipe with some stainless screws on top of that intended position on the chambers. Yeah, that's probably enough there, I think. Oh, I know what I was going to do. I was going to look at volume 3 for that same section, and that section was 6.5. 6.5. There, by the way, as I'm scrolling back, is all our watertight testing standards and what have you. There is a bunch of material on flotation. Sorry to change the topic here, but I missed this earlier, so I wanted to point this out. We were talking about risk of tank flotation, and this is helpful. First of all, it gives guidance on how to anchor tanks or drain them, but look at this. Here is a way of doing the math to determine if there's a risk or a significant risk of the tank moving around. Basically, it's a way of calculating the displacement, if that's the right term. You know, how much floating action is being applied by groundwater, and balancing that against the weight of the tank and the cover soil. So I think that's all I'm going to say about it, but it's kind of slick. I'm grateful for it, and if you look at it, probably on your own time, it's pretty simple math. It's sort of the way to decide what the floating tendency is and whether you need to do anything about it. You know, note in this example it says the tank will float unless there's 2,000 kilograms of soil on top of it. So it suggests we use a safety factor of 1.5. So we can calculate the weight of the soil. A guideline is 2,000, I guess, 2,000 kilograms per cubic meter. Is that what it is? Anyway, I'll move on. There's lots of data on how much soil weighs. What I was looking for before I digressed was a drawing of 6.5.2.3. Here it comes. 6.5.2.3 observation ports. Just to be clear, this is not that. This is an observation standpipe for groundwater, so it's going down below seasonal water table. The observation ports that the SPM is requiring only go to the infiltrative surface. like so. Would have preferred a different one. 3.6.6.1. I'll just keep scrolling. Here comes one. There's the diagram I was looking for. So here is a infiltrative surface observation port. So it's a hunk of pipe extended to the infiltrative surface with some holes in it. You know, either take a drill and put a dozen holes in it, the size of your little finger, or slits with a recip saw, something that will allow the effluent to enter that port if it's ponding on the infiltrative surface. Personally, I put them at least 1 inch below the infiltrative surface. And they should have provisions to prevent uplift, like a T on the bottom, or a toilet flange, or a hunk of rebar stuffed through it, or something, so that when the maintenance provider goes to remove the cap off the top, he or she doesn't pull the thing right out of the ground. So those are infiltrative surface observation ports. Obviously, if it's a chamber, it doesn't go to the bottom of the chamber, it goes to the top of the chamber, but since there's no drain rock, you can look in there and see ponding. This is meant to be for a aggregate trench. Okay, how's it going? 8:30. Oh boy, it's time to wrap this up, isn't it? As usual, it all takes longer than I anticipated. Trench infiltration systems 266.3. So that's volume 2, 6.6.3. A few highlights here, I guess. Trench width is there. I think this might be new on slopes. The trench width is limited to 60 centimeters. Gravity laterals have to be 50 feet or less. Coming out of the D box. Trenches have to be level. And what do we mean by level? We mean really level. We mean 0.17%. It's at 2 inches in 100 feet. They do have to be along the contour of the land. Remember, these are trench systems. Still seeing a lot of people running their trenches or beds down the slope. It's insane. I don't know what they're thinking. There's a spacing, still 6 feet, unless the slope is significant, in which case it's 3 meters. Do need to scarify the trench base. Do not over excavate and backfill, because now you've got a settling issue. Do not compact the soil, including the blinding layer. You're trying to scarify it and keep it loose so that it's infiltrative. There's some aggregate specs. Don't use 2.5 inch rock, even though you can. It's too big. 3/4 inch is good, unless you're using pea gravel. This is brand new. 6 inches below the pipe, not 9, and 2 inches over. So we just saved some money. So that is for drain rock meeting the standard in the box above. If it's pea gravel, it can be even less. So 6 inches instead of 9 inches. There's a big change. Cover soil. And here we go, 2 observation ports if it's a trench system, not a gravelless trench, but you know, again, for the chambers we need 1 for every lateral. If it's aggregate, we only need 2. Clear enough. What else have I got? Lateral length. Back to my slides to remind me of what I'm supposed to be saying. Lateral length level on contour, scarify, aggregate depth 6 inches, cover soil, been there and done that. Observation ports, 2 of them. Seepage beds, table 6, 7, 3, next page. So, what do we got? We got that this now is for beds, right? Seepage beds, and these things need to be level, really level, within 1/2 inch. We want the infiltrative surface to be level so that as it starts to clog over time, it doesn't create ponding. Right? So it's going to make more even distribution because the thing is level. Another reason to have a rotary laser and to have installers who know what they're doing. Any fill below the infiltrative surface has to be mound sand or clean coarse sand. We do have to prevent runoff from upslope using swales. Cover soil, no ponding. I'm trying to talk faster. Bed width, I missed it. Bed width was 3 meters. Sorry about that. Bed width, where did it go? Well, I'm not going to hunt it down now, I guess. 673. Oh yeah, it was back here. Beds have to be no wider than 3 meters. Maybe I went to the wrong thing when I was talking. Side to side within half an inch. Longitudinally 0.17%. They need to be level. I think we've been there and done that. And let's try to carry on. You guys are very patient. Sorry that my timing, it's taking way longer than anticipated. And crowned and grade. So this is what we mean. Is it's crowned, it's graded, there's no ponding, and it's suitable for grass. Right? I missed that point earlier, but I'm not going back there now. Is these things need to be able to support grass or other suitable vegetation. We need to do a good job of this stuff, and no ponding. Also, we need to manage surface flows, and that's why there's a swale here. Right? There's a path for any surface water to go away. There's another swale leading off in that direction. And this surface, hopefully, is perfect enough that there's no ponding. Usually what it means is a whole bunch of expensive landscaping, which is why we can't work cheap. Right? We have to bring in material, topsoil, lawn sand, and this takes a long time. It's also why we have to be competent excavating people or have installers who are, because otherwise this will take you 3 days to do this. I mean, this is a big job, raking off this amount of area. So the trick is to place the material really close to being perfect with the machine. Generally what it means is you're giving the client an entire new yard. And that's just the way it goes. You need to have that conversation. You need to explain. You could have it as an exclusion, but then they have to sign something saying they're actually going to make sure this thing is finished and grassed. Usually it means a new yard for the client. You have to fix all the disturbed areas, not just our dispersal system. I think I kind of went there because I was jumping around, so let's just speed read this. Shallow at-grade and raised systems. No, we didn't. We went to seepage beds, but not raised ones. So raised ones, it's the same stuff. They need to be level, half an inch side to side, 2 inches at 100 feet longitudinally. Any fill has to be sand media. Fill for cover soils has to be good stuff. What else have we got for... Yeah, we need to make this point. Is I'm going to go to volume 3, section 6.8. 6.8. So we need to understand, first of all, that these things, seepage beds, can be at or above grade without being a sand mound, right? But even though they're not a sand mound, they still have to have sand media fill on the portion. In other words, we can't haul in some good fill or some pit run or something like that to raise the system above grade. The reason we're doing this is probably vertical separation, but there you go. If it's above grade, it has to have uniform distribution. In other words, pressure or drip or something. If that fill, in other words, if we're raising it more than 30 cents, now it's a sand mound, and then we have to follow all the sand mound specs. Then I need to make this point, I may have made it in an earlier webinar, is a raised bed or an at-grade bed is not the same as an at-grade bed. Those are special things. There's two specific technologies for at-grade systems which are placed directly on the native soil, and those are at-grade beds in Alberta at-grades, which is not the same as a seepage bed placed at an at-grade elevation. A seepage bed has to be perfectly level, and all the associated standards with lateral spacing and all that would be as per seepage bed. An capital A at-grade bed or an Alberta at-grade is a different thing. Those are placed on the undisturbed topsoil, on the slope, on the natural gradient of the soil, and we'll see some diagrams of that. Well, how about right now? That is going to be, I'm going to see those. Nope. Okay. Bear with me here. I covered up some notes. 681, 684, 684. Tow blankets. Same story as a tow blanket from a mound sand. Can be permeable soil. It doesn't have to be mound sand. It doesn't have to be C33. Just needs to be reasonably permeable. Let's go back to my slides. A lot of content here. So again, don't confuse these at-grade systems with a at-grade bed or an Alberta at-grade. Have to be pressure. 3684 says that tows can be clean permeable fill, in other words pit run. Gravity dispersal. In the interest of time, I'm not going to go back and forth. It specifies the lateral pipe slope, which is level. Right? Gravity systems should be level, and by level we mean no more than 2 inches in 100 feet, sloping in the direction of fall. There does need to be solid pipe from the D-box to the laterals, to the actual drain rocker chambers for a gravity system. It's not right to start perforated pipe right out of the D-box with drain rock, because then basically as the infiltrative surface clogs, you can have water going back into the D-box and so on. CTDS, combined treatment and dispersal systems, you don't need pipe in the bed. So we're thinking mostly about the open bottom version of combined treatment and dispersal systems that then have drain rock bed underneath it. And in order to promote distribution for a while, the salesmen and others were putting 3-inch perf pipe in there. Don't need it, it doesn't really help. It's not going to be even distribution anyway. It's still going to overload the soil under the tank. Don't need pipe. Speed levelers are mentioned. We need them in D boxes to equalize flows to each lateral. D boxes have to be watertight, and they have to have an access provision to surface. I'm just going to move on, I guess. Oh, yeah, very cool, is it? Yeah, I'll be heading there myself. Gravity distribution in 3691. In 3691. The definition. Gravity means that the distribution laterals are not under sustained pressure during a dosing event. And that, in other words, they don't get up to full squirt or anything like that. So that includes dosing systems where the effluent is dosed to large diameter pipes by pump or other method, including some of the CTDSs and including a pump to D box. A pump to D box is not uniform distribution. It's not pressure dispersal. A lot of people, oddly enough, think it is. It's not. It doesn't make all the soil wet. Instead of coming out 2 holes, it comes out 10 holes. And it's, yeah. Where else are we going here? Dosing me. Yeah, that's all I got there, I guess. So, you know, once again, dose to D box is still gravity distribution. It's not pressure. It's not uniform distribution. Uniform distribution requires that every half square meter gets wet, the same amount of wet within 20%. So we're getting closer. Dose gravity systems, again, because of time, I guess, you have to moderate the flow velocity. So I'm not going to open up the SPM because it's getting so late. That means that the pump can send so much flow volume into a tank, or a D box for that matter, that it disturbs things, right, or causes preferential flow in the D box and so on. So by moderating flow velocity, we mean, for example, a 2-inch force main heading to the D box or a septic tank, and then a chunk of 4-inch, right, like a length, 10 feet of 4-inch, which then slows down the flow. Dosed gravity systems, the pump controls, pump chamber standards apply. You still need reserve volume. Now you need flow monitoring because it's dosed. Dose frequency is still important. Dose frequency is at least 1 times per day based on DDF. Dose volume is a flood volume. And again, because of time, I'm going to move on. We do need to look at this. This is 610.3. Some important standards there. 610.3. So we need to plan and adjust the system so that it squirts 15%, within 15% across the network, 10% along any single lateral. In other words, squirt heights have to be very similar. And that comes down to hydraulic design. A couple of things here. We got 60 centimeter squirt height when using 3/16 orifices or larger. And it's 150 centimeters if we're using smaller ones. Always was, not really a change, I guess. Dosing frequency, distribution uniformity. This is important. This is how we determine the number of orifices. It's 1 per every 6 square feet. So AIS divided by 0.56 meters squared gives you a number. That's how many orifices you need. A lot of people are missing that. This is new. We can now use tiny orifices, even for type 1. We used to not be allowed to unless it was type 2 or 3. They were worried about orifice clogging, but we've discovered with some experience that it's not an issue. If you've got proper squirt height, it's not going to clog. This makes it different for pump sizing. If you run into a situation where you do the math and you need a 1 horsepower pump, but just barely, try it all over again with 1/8 inch orifices, and you might find that you can get away with a smaller pump. Oddly enough, people are still missing this. Every orifice needs an orifice shield, whether it's up, down, or sideways. Have to have an orifice shield. Unless it's inside of a chamber and it's pointing up. If the hole is pointing up, then the top of the chamber becomes an orifice shield. But if it's pointing down, you need to have orifice shields. Pipes need to be level. Good enough. 8-inch orifice shields. Hydraulic design. I'm quite concerned that with the new SPM, hydraulic design is going to go badly because the vertical separation standards now require us to use very small doses, dose frequency in the range of more than 10 doses a day. So now people are going to do their hydraulic design incorrectly. They're just going to do DDF divided by 10 or 18 or 20 or 30 or 40 for microdosing, and then they won't get up to full squirt. They won't have adequate even distribution. There's very little content on how to do hydraulic design in this SPM. The old SPM had a bunch of content in the appendices, but it does say we have to document that. So in our filing documents, we have to actually show the math, full hydraulic calculations, total dynamic head, minimum required pump flow for squirt height, and all that kind of stuff. What else did I need there? That's probably enough for now. Hydraulic design is a big topic, including some of this stuff out of Volume 3. We have to get full squirt for 67% of the cycle, and we have to meet the soil dose frequency from the other standards. And those are contradictory. If you have 1.25-inch pipes, 50-foot long laterals, You can't get 10, 12, 14, 18 doses per day and still get 67% of the cycle at full squirt. So that's important to note, is 67% at full squirt means, as a guideline, at least 3 times the draining volume of the system. 3 times the laterals, 1 time the force main if it's draining. And then we have to balance that against the soil dose frequency, and if those two contradict, then we need to apply some strategies to balance that, to make that balancing act work. And in volume 3, they have some strategies to make that happen. 6, 10. Should have known better than to try to fit all this content in one webinar. 610 2.2. 2.2. Here's all the stuff that you can look at in your own time. 67%, full pressure. Here's how to do it if you're having trouble balancing that against soil dose frequency. One is keep the laterals full. I do that all the time, but I don't need to worry about frost where I come from. If you're up north, you can't do that, right? You can't drill all the orifices up. If you keep the laterals full, it takes less time to get to full squirt, so you have a better chance of getting 67% at full squirt while still meeting a dose frequency over 8 or 10. And that means the laterals have to be completely level. If it's a 1-inch lateral and it's got a 1-inch dip in it, it's going to be empty, right? So it has to be exceptionally level. You can avoid having this stuff, the force main and manifold, draining to the field by placing it lower than the laterals. You can use short, small diameter lateral pipes. Some of my friends in Prince George, their laterals are only 20 feet long and they're 3/4 inch. And 3/4 inch, yes, you can get jetting equipment down them if you have proper cleanouts. 1 inch is way smaller volume than 1.25 inches, and 3/4 inch is way smaller again, right? Because pi r squared makes a huge difference. So small, short laterals will allow you to have time dosing at 12, 18 doses a day, 24, 36, microdosing, and so on. So small, short laterals, quicker pressurization. The other is just to increase squirt height. If you've got a squirt height of 10 or 15 feet, that's going to pressure up much more quickly. So probably enough said on that. That is a difficult issue. It deserves a webinar all on its own. A whole bunch of content on freezing conditions. And again, since I'm so late, I'll just say that the way to deal with freezing conditions is drain the laterals after each dose with some of the orifices pointing down, and possibly draining the force main too. And if you're draining the force main back to the pump chamber, avoid draining it through the pump, because if the dose engages when the pump's turning backwards from this draining volume, you can break the pump basically. So we put in a check valve and then a 1/4 inch orifice or larger just past the check valve, and then it drains through that. So I think maybe we had this picture before. Draining the force main means no dips and doodles. Use a laser, right? It's draining from the indexing valve back into the pump chamber. There's a shot from the other direction, draining back towards the pump chamber. It's not a different direction, it's a different trench. So the pump chamber is in behind this pile here. So that's one way. Indexing valves. The entire network we want to drain, so this thing is going to drain from the indexing valve back to the pump chamber through a properly installed force main. And the indexing valve, very prone to freezing, it's going to drain because all these fittings are tweaked. They're rolled just a hair, right? They're rolled so that all these pipes will empty after a dose. Speaking of freezing, we've got some insulation in the bottom. We're going to fill this thing full of insulation. You can fill it up with fiberglass or styrofoam popcorn, and the lid needs to be insulated like so. Right. You can buy these kits, by the way, where all this comes pre-done, which is very helpful. Freezing, we've been here and done that, right? Sleeves, insulation, and poly barriers. Insulation over this is the manifold, not the dispersal trenches. Dispersal trenches are running off this way and this way. So even though those lines are meant to drain, they drain fairly slowly, so insulation to make sure that we're not freezing up. Treatment plants now need to be insulated, so you can see the styrofoam in the lid, but this is spray foam, right? Spray foam all around the treatment unit. Getting close. We skip drip system. Pumps. We do need a pump disconnect, lifting provisions, independent supportive floats, everything within 6 inches. Wiring has to be long enough to remove the pump and the floats, and we need an alarm on a separate circuit. So where did I get all that from? I got all that from volume 3, 6.12. 6.12.3. There was a bunch of stuff on hydraulic design. 6.12.3. You guys must be getting tired of listening to me yatter along here. Just bear with me. We're getting close. So the brief version is this. This wire, we need to have enough slack that we can pull out the floats or the pump. You need some slack in the wire. Clear as mud. You need an independent means of removing the floats, like a float tree in this case, piece of pipe with a float strapped to it, or weighted floats. We do need a vent hole, and this one is in the wrong place. That vent hole needs to be right underneath the check valve. You need a vent hole, otherwise the back pressure on the check valve, if the force main is higher, is going to prevent the pump from operating because the pump is pushing against an air slug. It's like pushing on a sponge, so you need a vent hole. We could go on and on, but these things need to be within 6 inches of the lid, the valves, the unions, and so on. Enough, I guess. We no longer need the spacer. You don't need a spacer underneath there. Yeah, probably enough for now, I guess. Here's one. Here's the terminology. There's alarm reserve, which is 50% of DDF, and then there's reserve volume, which is meant to keep the alarm from coming on frivolously. That's 15% of DDF. Time dosing, a whole bunch of content for you to look at on your own time for time dosing. We need a bigger pump chamber because we need this. We need the equalization volume. We need timer reserve volume and so on. So a bunch of good stuff in volume 3 for that. I think, yeah. I guess I missed the wiring. We need 2 circuits, which shows up in volume 2. We need 2 circuits, one for the alarm and one for the pump, the control panel and the pump. If it's a control panel, it will have both circuits going to the control panel, but within the control panel, it splits, right? One to the pump and one to the alarm. What did I want to get out of here? Connect all wiring, adequate length of cable. All this stuff is important, I guess, but we're running out of time. We do need a union. We need a rope or other beams to lift the pump out. We need weighted floats, independent support. I'm repeating myself, which we hardly have time for. All that stuff, talked about that. And I'm going to move ahead and wrap this up. I got a few more pictures. Pump chamber sizing for demand dosing is 1 times DDF. For time dosing, it's at least 2 times DDF. This is new. There's a new standard allowing surcharge to upstream tanks for the alarm reserve. You can look that up on your own time. But what it means is we can put our pump chamber deeper than the outlet. We can have the lid of the pump chamber deeper than the outlet of the septic tank, or equivalent to, and then that can become part of the alarm reserve volume. We could even theoretically have a bit of surcharge into the septic tank, although I'm not sure that's a good idea. It explains dosing terms, talked about all that stuff, indexing valves. Here's what we mean by some of those things. There's a union to pull the pump. There's a pump lifting rope. There is a weighted float arrangement. You can just see the weighted float behind, or the float behind the weight. There's a float hanger, and what else do we need? We have a check valve in here. Personally now I'm putting my check valves down there, but that's another story. So hopefully we've, oh yeah, the other issue is this is how we need to plumb our piping inside the pump chamber, up and then back down again, up to keep all this stuff within 6 inches of the lid. If we had the time, I was going to look at standards for indexing valve. The short version is indexing valves need a valve. They need a union so that you can remove this thing. They need a bunch of unions actually. Right? They should have clear pieces of pipe. This comes from the kit from these guys. Clear pieces of pipe, very hard to find unless you buy the kit, and that's meant so that at maintenance time you can actually visually see the thing shift from one zone to the other. Some indexing valves have a pointer on top that allow that to happen. The other point is indexing valves have to be at the high point of the system. It has to be above the laterals, otherwise the slightest bit of back pressure prevents the spring from working and the indexing valve won't be reliable. So this is the highest point of the entire system, is the zone valve, indexing valve. And we could have gone on. At-grade beds are a completely different thing, and I do want to show you what we mean. An at-grade bed and an Alberta at-grade is this. It's not the same as a seepage bed placed on the surface. 613, there's an at-grade bed. So an at-grade bed has a completely different set of standards. It doesn't have to be level, different drain rock depths and so on. That's an at-grade bed. An Alberta at-grade is another example of something that's not a seepage bed placed at-grade. Right? An Alberta at-grade is brand new in this SPM, and an Alberta at-grade has to be placed on the LFH layer, the forest duct layer. And it's on a slope and so on. It's an entire whole set of standards that we don't have time to get into today because I'm way over time. Okay, we're almost there, almost done. So the sizing of those things is different, configuration is different, they have their own standards. Alberta at-grade, different thing, has its own standards. And sand mounds, just a few more slides. Sand mounds do have to have uniform distribution. You can't do a gravity. You can't do a D-box to a sand mound. The sand mounds include a check for the basal area. You have to size the area of the sand infiltrative surface based on sand loading rates, mound sand loading rates. And then you have to check that the base of the thing is big enough that the underlying soil can receive it. A good topic for another webinar is sand mound design. And then all the other stuff is the same as for previous standards. So in other words, if you're doing a sand mound, you have to look at that section, but also the previous sections that dealt with dispersal systems general and pressure and so on. A few key points about sand mounds. They do have to be level. Aggregate depth is different. Aggregate depth is only 4 inches if it's pea gravel, not 6, not 9. Sand media specs are completely different. We probably should have made sure that we had enough time to go there, but we don't. You have to make sure you understand the sand media specs. Permeable fill for toes, 2 different types of observation ports, infiltrative surface and in the toes. It deals with cover depth, toe slope is 2 to 1. At least demand dosing is okay for a sand mound only if you're using type 1 loading rates, otherwise it has to be time dosing. And here's some more changes. Moisture content and soil damage it talks about. And let's have a quick look, because you guys got all night, right? 2.6.15. 2.6.15. Here's all our stuff on sand mounds. And I wanted to go to the installation stuff. Dosing, distribution, installation. It talks about do not use wheeled machinery on either the basal interface or the sand. You can't use skid steers and so on. It changes the gradation even of the sand. It has to be tracked machinery. It talks about scarifying the soil, absolutely. Minimum of 6 inches depth, it says, which I think is a bit harsh if you only had 10 inches, but that's what it says. It says sand may be gently mixed into the native soil. And that's our basal interface sand remediation. We'll have a look at that. The track machinery has to have sand under it. Right? When you're placing the sand, you have to be super careful you're not making the basal interface less permeable. Hence all those standards. Also, hence, you don't compact the sand. No vibrating compactors on the sand mound. You track pack it with an excavator. In other words, you settle the sand. And almost done. Did you believe me the first time I said that? Here is scarification and sand remediation. So we throw a little sand out there and scarify it again. Right? We're blending sand into the surface layer to improve its vertical receiving ability, to improve its permeability, make sure the sand mound doesn't break out at the toe. Right? There's sand remediation. Then we place the sand with a tracked machine, track packing it, or in this case, because the machine was so big, I just squished it with the bucket, frankly. I didn't get the tracks up there. But with that big machine, that's enough, right? Can squish it. That infiltrative surface needs to be super level. All this stuff doesn't have to be mound sand. Right? It can be pit run. Right? Pit run over, pit run all the way down in here, all the toes. And in the end, it looks like that. Sand mounds are huge. Right? This is because the underlying soil is clay, fairly big house, but mostly because the underlying soil was so bad. So that was really just to achieve the basal loading check, to make sure the underlying soil is good enough. And of course, linear loading is awful when the underlying soil is so shallow. So this thing, I think, was 110 feet long with an extended toe blanket. And when it's all over, it looks like that, except it hasn't been raked yet. And now we pretty much are done. There are other new standards for evapotranspir... what are they called? Evapotranspiration absorption beds or something like that. Lagoons, mostly the lagoon stuff is about preventing backflow, and there's new standards for site drainage. And that, finally, is it. So, again, we're going to stay online for questions and discussion, but if anybody wants to log out, feel free. And the recording will be up on the Learning Resources page eventually. So I apologize profusely for completely overestimating the time, but there we are.